Hi, I'm William Meyer. I'm an engineer at Troops, and I've been coming to NY Scala for years, and I'm really excited to be presenting. My talk is Implicit Class, Machinery Behind the Semantics, and it's about the compiler Scala C and how the implicit class language construct is transformed within the namer and the typer. So in the title, the language construct is the semantics, and the compiler is the machinery that we're really going to dive into and try and understand. So I work for Troops. Troops is building AI for work. If you've looked across your company and seen people that aren't on the engineering team, especially people on the sales team, doing things inefficiently, dropping the ball, not being on top of their work, we are building an AI that's going to help them do their job as efficiently as possible. We're integrating lots of different data sources. We're running really sophisticated analytics, and we're hiring. Please go to Troops.ai/careers. We're looking for senior Scala devs, and we've got lots of really cool work. So we'd love to hear from you. If you see anybody in a Troops t-shirt, please introduce yourself. So the goal of this talk is to understand the Scala compiler. We're going to do that by tracing the compilation of a simple program and concentrating on a single feature within the language. So there's an agenda, and what's the agenda? The first is, what is implicit conversion? You've probably all used implicit conversion, but we really want to understand a lot more about specifically what it is in the language specification. The next is our simple program. This is going to be result and rich result, and we'll look at the Scala code, and we're going to trace that Scala code as we can compile it in Scala C. Then we're going to talk about the compiler data structures and the different phases within the compiler, and then we're going to talk specifically about three major phases: the parser phase, the namer phase, and the typer phase. So what is implicit conversion? We're looking at the Scala language specification right now, and I'm going to paraphrase this quote rather than read it to you. But if we ever have e.m, we're selecting the member m of the element e, and e is of type t. If m is not accessible, doesn't exist is the most likely scenario, we're going to search for an implicit view that converts the e into some type that does have a member m. So an implicit class is defined in the Scala Improvement Proposal 13. It's syntactic sugar to define both a class and the implicit view in one place. So if you ever use the modifier, the prefix implicit before your class definition, when the Scala compiler finds that code, it's going to convert it into two things: a class definition and an implicit method that is going to convert our class, or convert the constructor argument of our class into the new class. So let's jump right into our simple program. So here's our simple program. This is kind of modeled after anytime you had to wrap a Java API that might return null. So we've got a class result. Result takes as a constructor parameter an integer, and there's one method get that returns that integer. You'll notice that that integer, the constructor parameter, could be null, in which case get would return null. So we've created an implicit class rich result that wraps result with a new method getOpt, and getOpt doesn't return a integer, it returns an option integer. And now we have our main program where we're actually going to make use of this implicit conversion so that we can call getOpt on a result. So right now we're looking at our sample program and what the sample program would look like after it's been compiled, desugared, and the implicit view has been applied. So the first highlight is the Scala Improvement Process 13. We're taking the implicit class rich result and we're creating an implicit view, a method that is implicit that takes the constructor parameter of rich result, R result, and builds a new rich result. The second highlight at the bottom is we're actually using the view. So we'd attempted to call, in our source code, we'd attempted to call result.getOpt. GetOpt is not a member of result. The Scala compiler found the implicit view def rich result and applied it to make the member getOpt available. So now we're going to talk a little bit about data structures. The first one, data structures within a compiler. The first one is a compilation unit. The Scala specification says a compilation unit consists of a sequence of packaging, import clauses, class and object definitions. For our purposes, it's broadly a source file. And a source file is going to be broadly an array of characters. That's kind of how the Scala compiler is going to look at it. The next data structure is the context. So there's a comment in the code that describes a context as a motley collection of state and loosely associated behavior of the type checker. That's always a good sign when you see a comment calling a class a motley collection of state. So a context holds on to the tree, the symbol, and the scope that are the current focus of the type checker. It also holds on to an outer context. So as the namer and the typer descend the Scala abstract syntax tree, they're going to create new contexts, and those new contexts will have a reference to their outer context. The context also holds any synthetic members. So synthetic members are Scala code, Scala AST nodes created by the compiler rather than written in your own code. So as an example, the implicit method created by the implicit class is a synthetic method. It's going to be added to the context list of synthetics and then later added to the source code. The next data structure is a tree. So this is our AST. It's an abstract class, but all of the implementations of the abstract class are case classes, so they're quote unquote immutable. The distinction is that trees hold on to both symbols, which is a type mostly created by the namer, and types. Both of those are mutable. So many of the tree case class implementations have methods to set the symbol, to set the type, and then to modify the symbol and type. What is a symbol? A symbol links definitions with references to definitions. So if you think of val r equals some value, the actual r, that's our definition. Any place that you would reference this definition is a reference to the definition. Both of those are symbols. So symbols have a name, which is a string, a position in the source file, and some flags, whether it's a method, whether it's a parameter to a method. The next data structure is a type. This holds all the type information that you care about. We're going to be mostly looking at the class info type, and that's going to tell us what are the base classes, what are the members. The way that a type holds onto its members is a scope. So a scope is a collection of symbols. Inside the compiler, it's just implemented as a hash table. And the most common way we're going to use the scope is we're going to look up a symbol by its name. So if we want to know if a particular class info type has a member called getOpt, we will say class info type, search for a symbol with the name getOpt. Context also has scope. That's the lexical scope of your program, rather than the hierarchical type information scope. So now we're going to talk about the compiler phases. The first one is the scanner, or the parser. This is implemented the exact way you would implement a parser in your CS 101 class. It is a scanner, which takes the array of characters and turns it into a stream of tokens, and a parser, which takes the stream of tokens and turns it into a tree. The next compiler phase is the namer. The namer takes the Scala AST, this tree, and creates symbols. Anytime it finds a definition, it's going to create a new symbol. Anytime it finds a reference to the definition, it will create a symbol. The namer is also responsible for some desugaring. So the desugaring that we care about in this presentation is the implicit class desugaring. We're going to create an implicit method. That happens in the namer. The last phase is the typer. The typer takes a tree and assigns a type to that tree. You can think about it as the result type of evaluating that tree in the Scala language. It's also responsible for inferring types and resolving implicits. So the typer is what notices that a result doesn't have a method getOpt, finds the implicit view and applies the implicit view. So we're going to start walking through these different phases of the compiler and really looking at what our sample code. So on this slide, we can see we've got just a bit of our sample program. It's the implicit class rich result. And the bottom half of the slide is the Scala AST. This is the parser has taken the compilation unit, the source file, the array of characters, and converted it into this tree. So the Scala AST looks a lot like Scala source code. It's a case class, and it's called classDef. ClassDef has some modifiers. In this case, the most important modifier is that this class is marked implicit. It has a name. So in Scala, there are two namespaces for types and terms. In this case, because we're defining a type, a class, the name is a type name with holding onto the string rich result. The next parameter, tparams, is the list of type parameters. Because our rich result has no type parameters, this is an empty list. And now we get to the implementation of our class. This is the actual methods that exist on a rich result and its parents. So in this case, you can see that rich result doesn't extend anything explicitly in our Scala code, but it does extend Scala eniref. So it has a list of parents, and it's only Scala eniref. There's no self-type, and now we're getting onto the body. So the body of a template in Scala is all the methods, all the members of that class. And it's going to continue on the next slide. So this class has two members. One is a valdef. It's the R constructor parameter. It's private. Because we didn't put val before R, the modifier is private. It has a name R. It has a type, but this is a tree type. This is not a type in the compiler. It's a tree that represents a reference to a type. So I hope you can read that. It's the ident type name result. And the right-hand side is the implementation. It's what is this definition equal to? In this case, it's equal to nothing. The constructor sets the value of R. R doesn't have its own value. It's not a method. It's not a field with an implementation next to it. The other member of body is the def. This is our method. It's called getOpt. It has no type parameters. It has no value parameters. And it has a tree type, which is option integer. But it also has the right-hand side. This one actually has an implementation. And we can talk quickly about what this tree means. The most important part is on the lower right-hand side, the select. So in the Scala AST, in a tree, a select is anytime you say e.im. You are selecting the member im from the instance e. The other important thing to see is apply. Apply, you can think of in your Scala code as anytime you have open parens. In this case, we're applying the option to r.getOpt. So we just finished the parser, and we took a little bit of Scala code, just a few lines, and converted it into our Scala AST. We're now entering the namer, and the namer is going to take this Scala AST and create names. And so this is the structure of the code within the namer. It's pretty straightforward. We have a dispatch function, standard intersim, and what that's going to do is case match on the Scala AST and call some subsidiary function, some ancillary function that will actually do the work for us. So we pass in our tree. In this case, the instance of tree is an instance of classDef. So our pattern, our extractor case matches, and we enter the function innerClassDef. All of these functions that take a particular type of tree and add symbols to it in the namer have this structure. For a classDef, the first thing we're going to do is create a symbol. This is going to enter the definition, the name, rich result into the context of the namer. You can see up at the top that the namer has one constructor parameter, in this case it's context, that we're going to modify through all of these different, all the methods within inside the namer. So the first line creates a class symbol, enters it into context.scope, and assigns the class symbol to the tree. The second line of innerClassDef creates the type for the symbol. So you can see where it says tree.symbol set info completer of. Often we don't have all the information we need in the namer to decide what the type of a particular symbol is. So we don't assign a completed type, we assign a lazy type. And later on in the namer or the typer, if we ever call this class, this tree.symbol.info, we're actually going to run a lot of code that will figure out what the type of this symbol is. The last part is where we do the desugaring. So at the very bottom where we say, does the tree have a modifier implicit? In our case, we know it does. Is the primary constructor arity 1? So we care that if we're going to do the implicit class desugaring, then the primary constructor of our class needs to have one and only one constructor parameter. It can have more implicit parameters, but one constructor parameter. And now we're going to, in the highlight, enter the meat and potatoes, enterImplicitWrapper. This is where we construct the synthetic implicit view and add it to our context. So enterImplicitWrapper. What we're going to do whenever we create a synthetic is we're going to create the Scala AST for a bit of code, and we're going to add it to our context. So in this case, we know we want to add a method. Well, what does a Scala AST method look like? It's a def. What are its mods? Well, in this case, we know it's a method, so let's put that on there. We know it's going to be implicit, so we add that, and we mark it as synthetic. What's the name of our new method? It's the same as the name of our implicit class, so we can take that right off the class def. What are the type parameters of our new synthetic implicit method? Well, they're the same as the type parameters of the implicit class. In this case, rich result has no type parameters, so that'll be an empty list. The value parameters of our method are going to be the single constructor parameter of our class. So there's a little bit of logic you need to convert a constructor parameter into a method parameter. And that's the first two lines in enterImplicitWrapper. And now we need the type of our method, the type tree. Well, we know what our implicit method, the type is going to return. It's going to return a rich result. That's the whole point. And what does the right-hand side look like? Well, the right-hand side looks like create a new instance of rich result, and the pass as an argument to your new rich result, whatever the arguments of your primary constructor were. In this case, our result. The last bit looks just like the code we saw a second ago in enter_class_def. We're going to create a symbol for our new method. We're going to assign a type completer, a lazy type, to our symbol. And we're going to take this Scala AST node that represents our implicit method and add it to the context. So context.unit.synthetics is just a collection of synthetic methods. In the typer, we're going to loop over that list of synthetic methods and add them to our tree and type them. So we're now passing from the namer into the typer. And what does the typer do? The typer assigns types to trees rather than assigning types to symbols. The typer is the most complicated part of the Scala compiler. What this slide is meant to represent is how big the typer is. You can see it's 5,700 lines. It's bigger than the parsers and the namer combined. There's 420 methods in this one source file. 150 of those are methods on the typer. The rest are inner defs. It's a big, complicated piece of machinery. So looking back at our sample program, the code we really want to concentrate on is the main method. This is where we're going to apply the implicit view. This is where the typer needs to recognize that result doesn't have a member getOpt, and it needs to find some way to turn result into a method into a type that does have a member getOpt. So we're looking at our main program, and this is the Scala AST for the line of code we're really, really interested in. It's our valdef. We are creating a new val called opt_value. We don't have a type on it. There's no type annotation. And its right-hand side is a select. It's a select of an identifier, or a qualifier, which is the name result, and a name getOpt. So the typer dispatch works very, very similarly to how the namer dispatch works. We enter in a function called typed, and we case match on the tree. Depending on what the tree is an instance of, we have different methods that are going to transform the tree. In this case, the tree is a select. So we're going to call typed select. What does type select do? Well, the first thing it's going to do is type the qualifier. In this case, the qualifier is an ident term name result. If we trace this program through typing ident term name result, we would call typed ident. And typed ident would take the name result and search context.scope. So if we remember from earlier, a scope is a collection of symbols. We usually look them up by name. All that typed ident is going to do is look in the context for a name or a symbol with a name result. If that name exists within the context, we're done. If it doesn't, it can search its outer context. So this is how nested scopes are represented. Anytime you create a new block, anytime you create an inner class, those are creating mini contexts. So looking back at the slide, once we've typed the qualifier, in this case we know it's going to be the result definition, and it's going to have the type result. We're going to look in the type result for a member called getOpt. So the way that member works is it looks on the scope of the type. So class result is a type, it has a scope. We're going to look up any member on result that has a name getOpt. And this is going to fail. It's going to return no symbol. So how do we fix this problem? How do we implement the implicit language, the implicit view feature? So what I've done is I've taken the code from the bottom of the previous slide and just moved it up a little bit because we're going to add the code that looks up an implicit view right now. So the highlighted part, the bright white part of the slide, is what happens when a type does not have the member we want. In this case, result doesn't have a member called getOpt. We just call or else. You can think of symbol like an option. You've called or else on it before. In this case, we say if there is no member on result called getOpt, then let's call adapt to member. Adapt to member is the actual code that looks up the implicit view. So how is adapt to member implemented? Adapt to member is implemented in a pretty clever way. We are going to create a type that represents the view we want. In this case, we know we want a view. A view is going to be a function from the type we want to the from the type we have to the type we want. So the type we want is any type that has a member getOpt. Let's see if I can. So the type we want is any type that has a member getOpt. So if you look on the lower right-hand side, we have this def getOpt. This is a refined type. It's not a class. It is a subtype of any other type. It's a supertype of any other type. It's equivalent to any other type. The only refinement we have on this type is that it has a method called getOpt, and we don't care what the return type is. That's what we want to get. What we have is the from type. It's a class result. So what we're going to do is create a view function. It's going to be a function one from the from type class result to the to type. The to type is any type that has a method called getOpt. And the actual implicit search is really, really straightforward. Context has a list of implicits, and so we're going to loop over those implicits and find any implicit that is a subtype of the pattern we're looking for of a view. A function from class result to a class with a member getOpt. So we're going to do this in Scala code, and the simplest way is a filter. The rest of this code is going to take the eligible implicits. These are all the implicits in scope that are subtypes of a function from a class result to a class with a method getOpt, and it's going to sort them. If there are none, then the implicit wasn't found and our code isn't going to type check. If there are multiple, then it's going to sort them according to the rules of precedence in the Scala language specification. If multiple implicits have the same precedence, this code will throw the ambiguous implicit error. And that is everything. You've just walked through the three major phases of the Scala compiler, and you've seen how we take the Scala code that you write into a tree, the AST. How the tree gets symbols assigned and how we desugar some of the implicit class construct into a class and a method. And then how in the typer we resolve a selection error, the inability to call getOpt on a result. How does we fix that? Well, that's the slide right behind us. And that is the end of the presentation. I want to thank Dustin and NY Scala. I've been coming here for a long time, and I really enjoy it, and I feel like I learn a lot. I want to thank Novus, where I learned Scala, and in particular, Brian Kim Johnson, who worked a lot with me on this presentation. And I want to thank Troops. Troops is my new adventure, and they are super, super supportive of being involved in the community. This presentation was a ticket in Jira, in our issue tracking system. It was something that they really, really encourage, and they want people to learn a lot and be a part of the community. Does anyone have any questions? So I followed a little bit of those threads. I know that as... Oh, thank you. Dustin had a question about Miles Sabin has made some changes to the type checker recently that are, I think, going to make it into 2.12, and that will significantly reduce boilerplate in some libraries that use higher kinded types. I've looked at the PR and the code, and Miles, I think on Twitter, made the point that this was a relatively simple fix, that someone on the mailing list had come up with a proposal for a solution, and all Miles had to do was go in, find the appropriate part of the code, and make the change. I'm sure the change is super useful, and I'm really glad it's going to be in 2.12. But I would say that making changes to the typer seem really, really difficult. The typer, as you've seen, there's a lot of mutable state. A tree might be immutable, but a tree has a symbol, and that symbol is mutable. A tree has a type, and that type is mutable. And a context is just a big ball of global state. And in the actual typers.scala, there's a lot of code. And so the most important thing to me coming out of Miles's work is just, can people start making changes to the typer? Can they feel confident that their changes are correct? Can lots of people make those changes? And I would say, based on my experience, no. Miles is a very particular case, someone that has a lot of experience and is great at what he does. Any other questions?
So the example you had, the val was unknown at the point of trying to do the implicit search. So you end up with an existential in your refined type.
So you don't end up with an existential. Sorry, is that the question?
Well, along these lines of you don't know what you're going to get, so you leave a blank about where you're going to as your return type. I interpreted the question mark as an existential, but that's not the case. And the question was, if you ascribe a type to your val, does that help guide the implicit search? I can't remember off the top of my head, but you can supply extra information in the context for the typer to restrict how much is going to search.
Okay. So one of the questions was the val def, where we said val result or val value, I think. It didn't have a type annotation on it. Let me find that Scala AST. Here, do you mean this type tree? Doesn't have an annotation?
Val opt value.
Yep.
Is no ascribed type to it.
Yes, there's no type annotation on opt value. From what I've seen, none of the, from the code I've traced, I've not done it with an annotation. I suspect there's no reason that it couldn't add that, replace the question mark in the refined type with the type annotation on opt value. It's not something that I would feel confident saying it does it or doesn't do. I do want to follow up on the one other piece about the question mark. So the question mark does look a lot like existential. In actual Scala code, it would be. In this case, it's a wildcard type. So wildcard types only exist within the compiler. They should all be out of they should no longer be in the compiler by the time you finish the type checker, and they have the property of being a subtype of every other type, a supertype of every other type, and equivalent to every other type. Slightly different than an existential, which is a particular type, but where you can't make any of those equality judgments. So an interesting thing is how this subtype method is called. So does everyone notice at the bottom there's a less than, colon, less than? That's a method, an infix method, that says, is the left-hand side type a subtype of the right-hand side type? The implementation of that method is actually incredibly complicated within the compiler. But there's a part of it where it says, is the left-hand side a wildcard type? Yes, then the subtype method returns true. Is the right-hand side a wildcard type? Yes, then this method returns true. The wildcard type is not something you can create in your own Scala code. It's something that you can create if you're creating ASTs by hand. Okay. Oh.
So the implicit classes, they have this ability to optimize some stuff out, right? Or at least that's what I heard.
So there's.
I'm wondering where does that happen?
So I think in the Scala improvement proposal, or the draft that became the Scala improvement proposal, there was some discussion about whether or not the compiler could optimize some of that machinery out. It's not something that I've seen in the Scala compiler, and I'd be surprised if it was implemented, but it's totally possible. The code seems really, really straightforward, and the PR for Scala Improvement Process 13 is actually very small, and it's by Paul P, and I definitely encourage you to look at it. It's not much more than reusing some of the case class mechanics, the case class syntactic sugar mechanics, to add a synthetic to your context. So I don't think it does any of the optimizations. It's possible it does.
So as far as you're concerned, it wasn't implemented, right?
I don't think it's been implemented. Sorry, the question there was implicit classes can be optimized, and does the compiler actually optimize them or not? Was that implemented?
I don't know if that's what you're referring to, but there's at least one key that is actually optimizes. When your implicit class extend and eval, it can actually be in line, and the object creation can be.
Okay, so if your implicit class extends any val, then the object creation can be, the compiler can optimize the implicit class. Rather than creating the implicit class, it inlines the method you're using implicitly.
Yeah, it will define a static method that the first argument is whatever the object would be from the constructor.
Mm-hmm.
You would call that directly instead of creating an object that would be useless.
Perfect, so it can be.
Is that done in the typer, or is it some other case?
So I guess I would suspect it happens in the typer, because the namer code, the enterImplicitWrapper, doesn't mention it, has no reference to that type of information. And the typer really has a lot more information and can do many more optimizations. Any other questions?
So, taking this like one step further, when you want to write like a compiler plugin, I guess you're just slotting yourself into one of these.
Yeah, so inside the compiler, you have a number of different phases. A compiler plugin is going to be another phase, and you can add it anywhere in the list. In general, you're going to add a compiler plugin past the typer. It's often really, really important to have type information. Macros is an example of something that's like a compiler plugin, often rely on that sort of thing. But you're not going to do anything more complicated than what this code does. You're going to take a tree, a bunch of case classes, you're going to case match on them to find the particular type of case class you care about, and you're going to transform it in some way. If you want to add new methods, you can add new methods. If you want to add a new synthetic class, you can add a new synthetic class.
So what's the practical decision maker for when you do a macro as opposed to this?
I would do a macro in almost any circumstance, in part because the documentation for the compiler is not very good, and the documentation for the reflection API and the macro API is much better. So yeah, I would definitely encourage people to use macros. There are some circumstances where people do want more information or a richer API than is provided by the macro. If you look at tail call optimization as an example, that's a phase in the compiler essentially implemented as a plugin, or as a compiler phase, a plugin, because it needs more information than a macro provides. Okay.
Thank you.
Thanks, guys.